was just that I was being a moron last time. And the command for making a listing file, I had the right flag, but I was just using the wrong program. I was using GCC, not the assembler. Okay, so the program that we use to assemble is AS, and this is the command for doing making a listing file. So hello, or AS for assemble, name of my assembly file, -A, that will tell it to generate a listing file, and then a greater than symbol, and then the name of the listing file that you want. Okay, so hello2.list or whatever here. Okay, so if I do that, two files are going to get created. This file called a.out, which you can ignore or delete. You don't need it. Okay, and then the other file is this new one, hello2.lst, and that has the listing in it. Okay, so if I open that, here's what it's going to look like. Okay, so it's basically assembly, but what else do we see over there on the left? We see basically memory addresses, or memory address offsets, really. So the program here begins with some data, and namely it's the string hello world, or, right? And there's the ASCII for it. Yeah. Okay, great. And then we've got our sections here, and then next to each instruction, it has the instruction, right, which we did in assembly, okay, but then it also has all of the actual encodings of those instructions, which we'll talk about what those encodings mean later, okay? But for now, think of this as a fancy assembly file. The assembler has just added some information to it. And so basically from here on, I want you guys to turn in the assembly source that you've written. So that's a .asm, an executable, and then an LST file that goes with the assembly for basically everything from here on, all the assembly projects, okay? And then there will be some of them where we'll need to also use that flush function, which you'll need to include because it'll be part of the program, but I'll show you how to link it in when we need it. Yeah.
Can you show that do the other one too? There was like a third one under that executable.
Oh, the executable? Yeah. Okay. So here I've got my assembly file, okay, the hello2.asm, okay? So the first step is I need to assemble it. And so hello2.asm, and I'm going to output this to hello2.o. Okay, so the O is an object file, and if I then if I look at what type of thing it is a 64-bit relocatable thing. So it's not quite an executable. It needs to be linked. And in particular here, it needs to be linked with the puts, because we were using that to output a string. Okay. All right. So that's step one, is assemble it to make an object file. And step two is to link it. And we can do that with GCC. So I'll do hello2.o output to hello2. And then I can execute as, oops, I did not mean to put the backslash there. And it'll execute like normal. Okay, so we don't have to use GCC for this last step. There is another program called LD for linker, and actually GCC is calling that as it does its thing. But I think it's easiest to just go ahead and still use GCC because we're using stuff from the C standard library anyway, so we might as well Like we're kind of still mixing C and assembly. Um, there is a way that we can do things like puts without actually using the C standard library, and I'll show you that at some point because it's uh, allows us to do a lot of other things that you may not have thought of that we can do. So anyway, there basically we're taking advantage of the fact that we're on a Linux system, but we'll talk about that later. Okay, all right. So do the steps make sense? Right? You type the assembly, and then you assemble it and link it, and that gets you an executable. And you assemble it to make the listing file, and that gets you your listing file. But notice that when I assembled it to get my object file here, I did not have the -a thing. So listing file is sort of done separately from the actual assembly. It's, yeah, kind of a multi-step process. Okay, and then if I look at the actual executable, I can see that this is in fact executable and dynamically linked and blah, 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 blah. Yeah, okay, so it's got all that info there. Okay, good. Yeah. All right, so now let's actually program some stuff. So let's do, if we go back to C, what did we kind of do at the beginning with C? We did our Hello World program. We managed to get some stuff printed to the screen. And then what? Huh? Yeah, we started taking input. We started doing things like we had a simple loop. We had some conditionals, right? And we were doing a little bit of math, right? Just counting up numbers or something. So basically, I want to kind of do the same thing, okay? But this time from straight assembly. All right, so let me do, make a new folder here in my programming. And let's do control, but in assembly. Okay, and what I want to contrast that with is the control structures that we had um, in C. Okay, so what were our control structures in C basically? Conditionals and loops of some sort. Okay, and so what we want to kind of look at is how do we start to implement those things in assembly. Okay, good. All right, so let's um, let's go here and let's make a new file for control and assembly. Okay, and get everything set up. Okay, so our main routine will be here. And what are the first two commands that we need to, or what's the very beginning of every program in assembly? Store pair, x29, x30, stack pointer, -16, exclamation mark. Okay, and later I'll explain what exactly that is doing here. And then the final instructions are load pair, x29, x30, stack pointer, 16. Notice the brackets, the lack of the exclamation mark and stuff, that actually means something. We'll talk about that later. Um, and then move W0, or sorry, yeah, W0, the number 0, and ret. Okay, so those are basically for our main routine. It should always have that in it, okay, at the beginning and at the end. Um, and if we don't have that, then stuff will get screwed up and pain. There will be wailing and gnashing of teeth. Okay. Okay. So let's do something where we can print a number, and so we can just do like a loop. All right. So I need a string. Okay, a format string to do printing. So what I want to do is print a number, okay? And let me just say this. So let's say we'll call this out string is ASCIZ, and let's make it the number is %I \n, and that's it. Okay, so this is a format string that has a %I thing in it because I'll want to print a number at some point. Okay, um, and yeah, and that's it. Okay, so we'll have to use printf when we print stuff this time rather than using puts, because we're not just putting a string, we're putting a string, but also putting in some data into that string. Okay, good? Yeah? Okay, so if I wanted to print a number, okay, the first thing I have to do is, so in C, if I wanted to do a printf, the number blah, blah, blah is, how would I do that? I'd have to do printf, parenthesis, what? Hmm? Say it again. Yeah, I could either type the string or I could just give a pointer to it, okay? But I would do pointer to string, comma, actual value of the integer, right? So if I wanted to print 5, the number 5, say, what I would have to do is I would have to do printf the name of the string and then a value for my integer. Okay, and 5, I'm just making up 5, nothing special there. Okay, so that's what I would want to do in C. Okay, in assembly, I have to do basically the same thing. Okay, but how I call a function and where I put the information to give to that function. Okay, so what information do I need to pass to printf? I need to pass the location of the format string and a number. Yes? Okay, so how can I pass, like what internal in the processor allows me to pass data back and forth? What is it that we're using? Okay, there's only 32 of them. Almost, but you're ahead of me. The registers. Okay, so data, the CPU processes data that's inside registers, and there are only 32 of them. Okay, how big is each register? How much data can each register hold? 64 bits, okay, at most. Okay, so this is why I can't pass a string by value. I can only pass it by reference, okay, because a string could be way bigger than 64 bits, right? Conceivably. Whereas what is definitely 64 bits, the memory address of that string, okay, so the pointer. Okay, so what do I need to give printf? I need to give it the location of the format string and also the value of the number 5. Okay, make sense? All right, so I need to put that information into registers. How many registers are there, and what are they named, even for that matter? How many are there? There's 32. Effectively, there's 31, okay, that we can really kind of make use of. Some of them have specialized purposes, okay, but what are these registers called? Okay, X0 through X31, okay, and the convention in Linux, at least, is if I want to pass data to a function, I do so starting with register X0. Makes sense, right? To use the start at the beginning. Okay, and the stuff that I need to pass to this printf function is I need to pass a pointer and a number. Okay, so the pointer is the location of the output string, the format string. Okay, and I need to put that where? I need to put that address in X0. Okay, so how do I put the address in X0? We did this last time. No? Okay, that's how we get a number there. Well, let's go back and look at it. Okay, this instruction right there. So we loaded X0 with the address of the format string. Okay, and how did we get the address of the format string? We put an equal sign in front of it. That's sort of like the ampersand symbol in C that gets you the pointer. Okay. Okay, so we need to put load X0 with the address of the format string, which in this case I called outstring. Okay, now, what else do I need to do? So if I just wanted to print the string, I could do that, and I would be able to printf. Okay, so let's do that and see what happens. All right, so let me assemble it. Get into the correct directory. Oh, sorry. And it's complaining because I don't have a blank line there. Okay, hold on. I'm making a mistake here. There we go. Okay, I just made some sort of typo. All right, so control, there we go. Okay, the number is -78, blah, blah, blah. Where did that number come from? Did I want to print that number? No. What did I want to print? 5 or something, right? But this is not the number I picked, 5. Okay, so why did that happen? Well, it happened because did I ever actually pass the value 5 to this function? No, okay? So what it did was it looked into the register number 1 for the value to be printed. Why 1? Well, the format string's address went in register 0, and I wanted to print a single integer, so it looked for that one in the next register, register 1. And what's happened here is that it's printed whatever just so happened to be in that register, but I never put anything there, right? So if I want to print 5, let me put the number 5 there. Okay, you don't have to have the pound sign, but it's good habit, so I'll just leave it there. Huh? Okay, and Patrick just noticed. Why did I do W1 and not X1? So, what's the difference between a W register and an X register? They really are the same physical location. The difference is, so X0 is a big 64-bit register, 64 bits wide. The lower half of it is called W0. Okay, so W0 is half of the X0 register. It physically is part of it. And the reason that this exists is because maybe I want to only store 32-bit data inside, even though I'm working on a 64-bit system. Okay, that's why the W's exist. They allow you to do 32-bit data at a time. Okay, so the reason here that I stored it in W0 is because in my format string, what format character did I use? I did %I, which means an int, and an int on this system is a 32-bit int. What about if I wanted it to be a 64-bit int? What would I have to have done? Instead of I would have had to have done, no, D is decimal, okay? And double is not the right data type here because that's a floating point number and this is an integer, okay? So so it'd be a long int, right? Okay, what's the print format thing for that? %li for long integer, okay? But here I just did 32 bits, so it's okay. Now, you might ask, why did I not move it to W0, right? So, easy misconception, W0 and X0, are they the same thing or are they not the same thing? They're not the same thing, but they kind of are the same thing, okay? They're not two, it's not as if there's a bucket over here called W0 and there's a bucket over there on the other end of the room called X0, right? The W0 bucket is the lower half of the X0 bucket. Okay, so imagine that you have a bucket inside of a bucket. Okay, so if I put the number 5 into W0, I would be nuking half of the data of the pointer to my format string, and stuff would get screwed up. Okay, I'd get a seg fault probably. Okay, so yeah, so X0 W1 is the next available register. Okay, does that make sense? All right. Okay, so now if I reassemble this and relink it and rerun it, it prints the number 5. Okay, that's good because that was the number I chose. Okay, nothing special about 5, it just picked something. Yes. It's just whatever happened to be in the register. W1, right? So now, why did it go looking in W1? Well, because the format string told it, hey, you need to be printing an integer. And printf knows that it should accept data. Format string's address is always an X0, right? That's the very first thing it's got to have. And then for any subsequent piece of data, it looks at the next register in order. So if I wanted to print like 6 numbers, I would have %I, 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 whatever, okay? And what it will do is look in register 1 for the first number, register 2 for the second, 3 for the third, and so on, okay? It does them in order, which is logical, I would say. Yes? To kind of go in order seems reasonable to me. Yeah? Okay. So, great. We just printed a number. Let's do some counting, shall we? Sound reasonable to do some counting? Yeah? Okay. So, let me put some space in here. Okay, and let me just start with the number, well, how about 1? I'm going to put a label here called add. So a label is not really a function by itself, okay? This is how we can do things like loops, okay? So right now, if I assembled and executed this code, it would work exactly the way it did before, okay? But let's say that I do the following. Okay, I add this command here, b add. What B stands for is branch, okay? Which means basically I want to go to the label called add and start executing instructions there. All right, now, how many of you guys took CS-242 at some point in the past or are in it now? Okay, is anybody not taking it or is not in it now? Okay. Has anybody ever programmed in BASIC? The language called BASIC. Has anybody even heard of the language called BASIC? Okay. Where have you heard of it from? It's older, yeah. Okay, but in particular, like, so what was everybody's first programming language that you learned? Okay, Python, but let's say before you got to college, what was your first language? Oh, batch, yeah, bat files, okay. Yeah,
Is that the one? Is that the one where like you have like numbers?
you have line numbers. You have line numbers.
Yeah, and you like have parts of the program that say go to like, and it's like one of those features where number books where
It,
like it goes.
yeah, kind of. That's actually a good way to think of it. It's like choose your own adventure programming, but the program chooses its adventure, not you, right? So, now, how many of you guys had like TI graphing calculators when you were in school, right? Did you ever program them? No? Oh, goodness. Huh? You were never allowed? What do you mean you weren't allowed?
They got mad at me last week, but they checked our calculators.
Well, they did that to us too, and we did it anyway, right? So, in particular, one of the very first things that a lot of us programmed when we were in algebra was a quadratic formula program, right? And the fancy of us made it so that it could even handle the case when there were going to be complex numbers and it would print all of that correctly. Like, yeah, it was great. But we were programming in a language called BASIC, okay? And in BASIC, it's like Austin said with the Choose Your Own Adventure, like books that you might have read when you were a kid, where it's like, if you want to go through the door, go to page 30. And if you want to leave, go to page 50 or whatever, right? So imagine a programming language that's sort of written like that, where you could say under certain conditions or under no condition at all, go to this page and start executing the instructions you find at that page, okay? So that's kind of how labels work, right? I've put a label here called add. Now I could have called it anything I wanted, okay? But what I've done with the instruction b add is say, okay, go to the page called add and start executing the instructions you find there, which what happened to be that set of instructions? The print command and the add. So what have I set up here? An endless loop, right? This thing's going to print and then print and then print and then print and then print and print and print and print, and it will never terminate. Okay. Now, obviously, do I want to have an endless loop? Probably not, but let's see what happens if I run it. Huh? Uh, no, you mean to call the label add? No, I could have called this anything I wanted, like, no. Like, add could be defined later on down in the program. Yeah, it just goes back and does it again. Right. I mean, imagine a choose your own adventure page where at the bottom of page 30 it says go to page 30. And so what would that mean? You go to the top of page 30 and continue executing. That's exactly what's happening here. But I could have called this anything, right? Now, obviously, if I can call it anything, I might as well call it something that's a logical or indicative of its function instead of something like Jabberwocky. Huh? You've never heard of this poem? Oh my. Okay. Let's take a liberal arts pause for a moment. It's a poem by Lewis Carroll. Yeah. 'Twas brillig, and the slithy toves did gyre and gimble in the wabe, and mimsy were the borogobes, and the momrass outgrabe. Touche. Yes. Beware the frumious bundersnatch. It's nonsense. Most of these words are just made up, right? So, no, it's not like assembly, Patrick. Okay, so let's see what happens when we run this. All right, so assemble it, link it. Did I forget to save it? Um, oh, yeah, thank you. Okay, so seg fault, good old seg fault. Okay, so what is a seg fault? Because some of you have run into this. It is. A seg fault is a segmentation fault. Thank you for that astute observation. Okay. All right, so what is a segmentation fault, pray tell?
Assuming that the Jabberwocky is a segment that failed.
No. No, the Jabberwocky is not a segment that failed. Okay, so when you are executing this program, or the computer is executing the program, right? We've discussed that you are allocated memory by the operating system. It's as if your program is given a little sandbox, okay? And under certain circumstances, your program can ask for more sand, but it can't have all of the sand. And in particular, there are other kids that have their sandboxes and really don't like your program, and you are not allowed to play in their sandboxes. Okay. In particular, you're not allowed to play in the sandbox that the operating itself needs to run because, well, that's going to start screwing things over. Okay. So you don't want multiple programs accessing the same sandbox worth of data. Okay, so segmentation fault occurs whenever you are going outside of your sandbox. Okay, if I go outside my sandbox, then bad things happen. Okay, now when does that occur when you're programming in C or in assembly? Like what situations are you trying to go outside your sandbox? In C, the number one way that you guys will get a seg fault is by messing up a pointer, okay, or using something that's not actually a pointer. So, for example, let's say that I wanted to print or I wanted to get scanf a number, right? What do I have to give scanf? I need to tell it that it's going to be accepting an integer, so I need to give it a %I format string, right? But then I also have to tell it where I want to store that data, okay? And what did I have to do with scanf? I had to give it, do I give it the name of the integer or do I give it the pointer to that integer? I have to give it the pointer. And if I don't, like, so let's say that integer, the number that I'm asking for input is 0, okay? And it starts as 0, but I'm going to ask the user to replace it with some number of their choosing, okay? If I give scanf 0, it's interpreting that as the location to put the number that the user types in memory address 0, which is not in your sandbox. Okay, so why did this happen here is a little bit more subtle. Notice, did it actually print a number? So when did the segmentation fault actually occur? Not the first time we printed, but rather the second time we tried to print. Okay, and the reason that happened, let me demonstrate with, so let me change a couple of things here. Let me add in the debugging. And statically link it. Okay, so I'm going to step through. Okay, I am now about to execute the printf command. Okay, what are in my registers? Okay, what's in register X0? Okay, it's some number. Yeah, 48A048. Okay, whatever. But what should that be? That is a pointer to where? It's a pointer to the format string, right? To use printf, I have to give it a format string, and that's the location of it in memory, whatever it is. Okay. What is in register X1 or W1? The number 1, which is the number I chose. Okay, good. All right, so I'm about to print. Okay, so the number is 1. All right, it's about to advance, jump back up to restart doing Jabberwocky. Okay, so I just finished printing, yes? Let me look at the registers now. What's in them now? The first two are the only ones we really care about here. Yeah, 16 and 0 or 10 hex. So what happened to my number 1? And what happened to my pointer? They gone. Okay, why did this happen? Not just why did it happen, but is it a good or a bad thing that it happened? Okay, so what happened is that the second time that printf tried to run, it tried to go to memory address 10 to find a format string. Well, that memory address is not in its sandbox. So the operating system said no and slapped our program down hard. Okay. It's kind of like, so you guys know John Barker? Yeah, we were talking about Rust, the operating or the programming language the other day, and how he had messed around with it a little bit. And he described it as, okay, it's like programming in C, but the compiler, anytime you try to do anything that's remotely unsafe or bad, it's like in, how many of you guys have seen the first Jurassic Park movie, right? What was the computer that the guy had when you tried to do something? You know, it would go, right? That's the compiler. Okay, so essentially that's what's happened here is the operating system has said, you can't go to memory address 10 and find a format string. Okay, so what this means, okay, is that the registers are what we call volatile. Okay, it means that subroutines do not have to preserve them. Okay, so there's actually convention in Linux. Some of them, the programs are obligated to preserve, and other ones they aren't. And it just so happens that X0 and X1 are volatile. Okay, so printf. So think about it this way: how many registers are there? Basically 32, right? And every program needs to use them, right? Including printf. That's a program, and so. And it's only got 31 of them to work with, which sounds like a lot, but for a real complicated program, maybe isn't. Okay, so it's going to use all the registers it has available to it, starting with the first ones. Okay, so the register's contents are not obligated to be preserved by subroutines. And that's exactly what happened here. We called a subroutine, namely printf, and it jumbled up all of our registers. And then when we tried to print again, it didn't work. Okay, so what's the solution to this problem? Because I still would like to print a bunch of numbers. Okay, I could use different registers because there are some registers that programs are obligated to preserve. Okay, meaning that if they change them, they're obligated to put them back to the way they were when the program started. Okay, so there are some of them that are obligated to be preserved. The other option would be we could take our number, the number 1, and put it someplace safe. Okay, a non-volatile register would be a safe place. What would be another safe place besides in a register? Well, we could put it out in memory someplace, right? Because how much memory do we have? How much RAM is on your Raspberries? Either 2 or 4, anywhere from 2 to 8 gigabytes, right? But point being, you've got gigabytes worth of memory. And all we're trying to do is store a piddly 32-bit integer. Okay, so let's go with the approach of the non-volatile one. Okay, because we'll talk about memory access later. Okay, so let me go back to here. Okay, so what I'm going to do is before I print, I'm going to make a copy of my number and put it in, let's see, actually I want to put it here. Okay, and then I'll delete this. Okay, so what does this instruction do? What do you think? Yes, it moves whatever's in W1 to W20. Okay, and when I say move, I really mean copy because the number's still in W1. Okay, but we just call it a move. Okay, does that order feel backwards to you? Okay, and that is just the order that most of these instructions are in, is the destination is specified first and the source is specified second. Okay, so that feels backwards. Yes, just get used to it. Okay, sorry. Okay, so what that has done is put the value 1 is now sitting in 2 registers. it's sitting in register 20 and register 1. Okay, so if I wanted to print whatever's in register 20, I need to copy it to register 1. Okay, the other thing I need to do is we saw that register 0 got nuked by the print function. So every time I'm about to call the print function, I need to put the address of the format string back into the print function, or back into the 0th register. Okay, good. All right, so let's run it now. Okay, so do you see what we've changed? Yeah. All right, so symbol, GCC. Okay, so now what's happening? Yeah, infinite loop. Okay, it's printing the number 1 over and over and over again. Okay, now is that all that interesting to print the number 1 over and over again? No. Okay, what could we change here to make this more interesting? I could add 1 each time. Okay, and I can do that by adding the number in W20. I could add 1 to the thing that's in W20. Okay, so what should print each time now? Should be a counter, 1, 2, 3, and so on. Okay, so let's see. Okay, can't do that. So what I have to do instead I can't add a number and a register. But what I can do is put a number in a register and add it to another register. Okay, so I'm going to put the number 1 in W1, add it to what's already in W20, put the result back in W20. And then when I come back around, what's the first thing I do? Move whatever's in W20 back into W1. Okay, so the first time what happens, I have 1, and then 2, 3, 4, and so on. Okay. Okay, so now what's happening? It's counting up. It's just going really, really fast, obviously. And it would continue going basically all day long. Okay. All right. Well, I've made an endless counter. We probably want to do something that's not endless, right? So how should I decide whether or not to continue looping, right? Basically what this means is I need to know how do I do some sort of conditional expression, okay? This branch here is called an unconditional branch. Did I ever decide whether or not to branch? No, okay? It just always branches, so this is like go to. But when Austin mentioned the Choose Your Own Adventure novels, do they ever just say go to page 50? What would be right before those words? Some sort of condition, like if you want to go through the door, go to page 50, and if you want to go through the window, go to page 55. Okay, there's some sort of condition as to whether or not you actually make the jump to the new set of instructions. Okay, and that's exactly what we need here, is we need some sort of way to do a conditional jump. Okay, All right, so let's just pick a number. How much do we want our counter to count up? To 20. Okay, great. So I'm going to put the number 20 into register W21. And actually, let's just, so my OCD doesn't freak out, let's go up to 21. Is that okay? Yeah. So let's count up the numbers 1 through 21. Okay? So I'm put the number 21, basically when I want to finish, in W21. Okay? And then what I'm going to come down here and do is I'm going to make a change. I'm going to get rid of this line. Oh, and let me change this, by the way, to 64-bit ARM so it'll color code it nicer. I want to compare what's in W20 with W21. Okay, so I do a comparison. Okay, that comparison really is going to be doing a subtraction operation. It's going to subtract one of them from the other and then look at what happens to the result. Okay, we'll talk more about the details of that later, but for now it's just going to compare them. And under what conditions do I want to stop looping? When it hits 21, okay, when my counter hits 21. So in this case, the condition under which I want to stop branching is when they're equal. And so I would continue looping if they are unequal. Okay, so I will do branch.ne for branch on not equal to Jabberwocky. Okay, so what that means is it will compare these two registers, and if their values are different, it will jump back up to Jabberwocky and continue printing. If they are equal, it will just go to the next line of code. Okay, so it will just go to the next instruction. Does that make sense? Okay, so in the Choose Your Own Adventure book example, let's say you get down to the bottom of a page and it says, if you want to jump through the window, go to page 30. Otherwise, what would you do? Just keep reading whatever's on the next instruction. Yeah? Okay, so that's what's going to happen here. All right, so let's redo this. Okay, and it printed up through 20, not 21. Why? Huh? I added after I printed, exactly. Okay, so if I wanted this thing to count up to 21, what would I actually need to put here? 22. Okay, so sometimes you have this off by one issue, and it's all about the order, right? Because like I said here, when did I print, or sorry, when did I add? After I printed, not before. Okay, and so I printed 20, then I added to get 21, and then it said, oh, they're the same, keep going, right? So I have to kind of take that into account. Now, there are condition codes for this. So for example, if I changed this to LE, that stands for less than or equal, oops, then it does print 21. Okay, so the reason there is because when the value is 21, is 21 less than or equal to 21? Yes, and so it re-executed one more time. Okay, so this is the difference, right, of inequality symbols when you guys are doing for loops, right? So when you set up a for loop, what are you doing? For I equals 0, I less than something, I plus plus. Well, you could have done less than there, you could have done less than or equal to. You could have done greater than even, who knows, right? But you could have put any Boolean statement there. And sometimes you did less, and sometimes you did less than or equal, and you just did whatever made sense. Well, we have basically the same flexibility here, okay? The other thing is that I would say is that the structure I've set up here is really more like a while loop, or even more so like a do while loop, okay? What's the difference between a while loop and a do while loop? A for loop is sort of a special example of a while loop. So what's the difference between while and do while? Yes? Other way. Right. So all loops need to have a Boolean condition that determines whether or not the loop continues. Yes? And the difference between do while and while is when you check that condition. A while loop, you check it before you execute anything in the loop body. A do while, you check it after you've executed everything in the loop body. Okay, so it's a matter of where you're putting your conditional, at the top or at the bottom. Yeah? And you could structure your program however, right? You have both things. A for loop is a special case of a while loop, right? Because you are checking, there's still a condition that you check and you put that at the top, not at the bottom, okay? Now, do you guys use do while loops all that often? Probably not. You probably mostly use true while loops where you check the condition first, okay? How have I structured this though? I've structured it here to check the condition after, okay? So I can change this to make it check the condition at the beginning instead of at the end, right? So let's redo it so that it's in that form. Okay, so you see how I've got b.le? I don't have to put the dot, but I like to. It makes it more readable. And this is branch on less than or equal. Okay, so there are a lot of condition codes for that. I can branch on less than, LT, less than or equal to, LE, equal to, EQ, not equal to, NE, and there's a bunch more, okay? And you just look up the one that you need, okay? From the sort of list of all the available ones. Okay, does that make sense? Huh? I don't have it handy at the moment. Um, most of the ones that you're going to use are pretty logical, right? Like less than is LT, less than or equal to is LE, right? Like they're basically going to be what you think. Yeah, I've got the list, but I don't have it handy here. Yeah, I've got, actually, hold on, maybe I do have it handy on my computer here. Oh, would help to look in the correct directory. Here we go. All right, let me switch over to my Mac. Okay, so here is a quick reference sheet, and I'll post this to Canvas, that has basically most of the instructions that you'll ever need to use in terms of the ARM programming. Okay, but the branch instructions, the condition code, and then somewhere on here is a list of the condition codes. Here they are. Here's all the condition codes. So equal, not equal, carry set, carry clear, minus, plus, overflow, no overflow, high, less, lower or same, greater than, less than, greater than, or equal to, less than or equal to, and always. Okay. So some of these, like the overflow or whatever, the carries and stuff, we'll talk about those later. Okay, but the arithmetic ones here, equal, not equal, those sorts of things, are kind of the things you'd expect there to be, because they correspond exactly to an inequality or an equality that you would use in C, right? If this is equal to this, then blah, okay? Okay, and you don't have to put the dot in front. I often do just because it makes it a little bit more readable to me, but that's optional, okay? Now, how these condition codes work, okay, is so when the comparison instruction is executed, what it actually does is subtracts one number from the other and discards the result. It doesn't care about the answer, but what it does care about is what flags are set. Okay, so in addition to your 32 registers, the processor has a special register called a processor status register. It includes various bits in it, and each bit has a particular meaning. Now, for the conditions, there's 4 of them that are important: the N flag, the Z flag, the C flag, and the V flag. Okay, the N for negative, the Z for 0, the V for overflow, and the C for carry. Okay, so how do I know if 2 numbers are equal? If I subtract one from the other, what should I get? Okay, so anytime you do an arithmetic operation, let's say that I did that operation and I got 0, the comparison is going to set the 0 flag, that bit, to be a 1 to indicate that the result of the last arithmetic operation was a 0. And then the branch instructions are looking at those flags, one or more of them, to determine whether or not they do it. So branch on equal would look at the Z flag and say, is it a 1? If it is, I'll jump, otherwise I won't. Okay. Now, when do the flags get set? With that comparison instruction. Okay, that's why we needed to have that. And as you can see, there are some of these that use more than one flag to make a determination. But the sort of basic arithmetic ones, like the 0, like branch on equal and branch on not equal, are pretty obvious. Okay, does that make sense? Sort of. Okay, so that's how it's actually doing it, and I'll post this this sheet up on Canvas. It's from somebody at, I think, like Penn State or whatever made it for their class, and I just stole it because, well, yeah, yeah. In fact, maybe it has a thing on here that who made it. No, it doesn't. Okay, so I don't remember who made it. But actually, on the subject, so thanks for making me look this up. Remember I mentioned that some of the registers are volatile and other ones aren't? Well, here's the list as to who's volatile and who's not. Okay, so for example, you see the ones that say must be preserved. Your program, okay, if it changes those registers, has to put them back the way they were when it started. Okay, or else bad things happen. Yeah, so we'll talk more about that stuff later. But the moral of the story is, don't count on your registers being preserved, right? And so what that will mean is we'll have to start storing data to memory in order to preserve it. Okay, so let's go back to here, okay, and let's change the order of this code to make it a true while loop where we do the checking at the beginning rather than at the end, okay? So what I would do here, okay, is I would do the comparison here. I would compare W20, which is my counter, with W21. And I want to branch on, well, let's see, if it's equal, then I want to, then I'm finished looping. And I'll call the label that I'm going to go to end for just something, okay? And then down here, I'll put end. and I'll remove this comparison and that branch. Okay, so now what's going to happen is W20 initially has the value 1 in it. W21 has the value 21 in it. And I'm going to compare them, and if they are equal, I'm going to jump down here to the label called end. Otherwise, I'm going to go into this bit of code and run it. Okay, then there's one other thing I have to put down here at the end, just before, or at the end of the loop body. I need to get back up to the top of the loop body in order to check, right? So I need to get back to this instruction, or rather this instruction, a comparison. Okay, so I'm going to put another label there, and I'll call it check. And here I need to do an unconditional branch to check. So that will take me back up to reevaluate, do I need to continue looping or not? Does that make sense? All right, so let's run this and see what happens. Okay, what happened this time? Why did it only print up to 20 and not 21? I checked after I added, but what branch condition did I choose? Equal to. So when so it added, and W21 had the value 21 in it. I just never printed that. Okay. So if I wanted to print that, what could I change here? I could make this greater than, okay, or I could change that to 22. Right. So either way, right? Okay. So is this kind of starting to make a little sense? Yeah. Okay. All right. I'll give you guys a nice little assignment of some sort, something exceptionally devious. Yeah. So okay. All right. Have a good one. I'll see you guys Thursday.